Hello and welcome to NH Tech. Today, we're going to design a Wilkinson power divider using Keysight Advanced Design System. Let's begin by understanding the basics. A Wilkinson power divider is a passive microwave circuit that splits an input signal equally into two output signals. What makes it special is that it maintains matched impedance at all ports and provides high isolation between the output ports. This makes it extremely useful in RF applications where minimal signal loss and interference are crucial. Here is the basic schematic of a Wilkinson power divider. It has three ports. Port 1 is the input, ports 2 and 3 are the outputs. The design consists of two quarter wavelength transmission lines, each with a characteristic impedance of approximately 70.7 ohms that is under root 2 times the characteristics impedance, which is 50 ohm in most cases. It also consists of a 100 ohm resistor connecting the two output arms. This resistor plays a crucial role by providing isolation between outputs and ensuring that the circuit remains well matched under balanced load conditions. Now that we've understood the fundamentals, let's move on and start building the schematic of this divider step by step in ADS. Create a new workspace and name it something like Power Splitter. Inside the workspace, create a new layout. From the left menu bar, navigate to Transmission Line Components and select the microstrip T lines. Now the first step is create a substrate. As I am using Rogers 4350 substrate, check if it is present in the list. If not, then add it from database. Select the Rogers 4350. Now select it from the list. Now set the two things. First thing is the thickness of substrate, which is 0.17 in my case. And the second is the thickness of copper cladding, which is 17 micrometer in my case. These values are taken from the datasheet, and this is the datasheet. Let's place a microstrip line. Now, what will be the line thickness? For this purpose use the Controlled Impedance Line Designer tool. Now, set the frequency to 12 GHz. Check the Optimize button as we want to optimize the line width for our substrate. So the result is 0.354. Now, set the width and length to 1 mm. Now insert a microstrip T and set the width to 0.354 mm. Now, adjust the orientation of the T. Now in the text step, we have to create this lambda by 4 path, with the impedance of 70.7 ohms. Now use the Controlled Impedance Line tool to find the width of microstrip line, optimize for 12 GHz, and set the impedance to 70.7 ohms. Again optimize. The resultant width is 0.18. As the total length of the circular path is lambda by 4, so we need to know the value of lambda at 12 GHz frequency. Use online frequency to wavelength calculator. So the value of lambda is about 25 mm. Now, place a microstrip curve. Set the width to 0.18. and angle to 180. Now, what will be radius, as lambda is 24 mm? So divide it by 4 to get lambda 4 and use circumference of circle formula. and divide it by pi to get the radius. Subtract 0.5 from the length, that is to compensate the access length from the t and other access lengths. Now, this half circle has a length of lambda 4 and an impedance of 70.7 ohms. Use the Shift plus X command to flip it around the x-axis. Next, create the two arms for mounting the connector. Now place port 1, port 2, port 3, and ports 4 and 5 for placing a 100 ohm resistor. To simulate this, we have to use EM circuit co-simulation. As I explained in my previous video, for this, you need to create a layout component, then place its symbol in the schematic and place a 100 ohm resistor and run the simulation. But before using this method, I'll show you a trick on how to simulate this layout without using EM circuit co-simulation. Go into the port editor, merge ports 4 and 5, and change their impedance from 50 ohms to 100 ohms. The next step is to create the EM setup. Set the frequency range up to 20 GHz. All other settings can remain as default. Save the settings and run the simulation. Here are the results. Observe that the return loss is less than -13 decibels, and S21 performance is also good. Now, let's also check the results using EM circuit co-simulation. When performing EM circuit co-simulation in ADS, there are two extra steps you need to follow in the EM Pro setup. The first step is to save the model. Go to the Model tab and make sure to check the box to Save the model that contains the results of the EM momentum simulation. This step ensures that the simulation data from the layout is saved and available for co-simulation. And second is the symbol creation. In the main menu bar, navigate to Symbol and select Create a symbol for the simulation. This symbol will represent the EM structure in your circuit design. You can modify the view or the scale factor of the symbol, but for now, I'll go with the default settings. This is the symbol that will look like. Save the setting.